Dillon Brout from NASA Einstein Fellow at the Center for at the Harvard Smithsonian Center for Astrophysics. Still there? Okay.
Yes, thanks. Okay, so this isn't the last talk, but I think we should still give Gautam and the organizers and our hosts a booming round of applause. How about that? So I realize there's just a couple more talks between us and the end of the conference. So it's been really fruitful. I'll try to keep my talk fairly succinct and hit really just kind of the highlights of what we found from 1,550 Type 1a supernovae in the Pantheon Plus compilation of Type 1as. So just briefly, if you've not been paying attention to how we actually do cosmology with 1As, well, even going back to the original Nobel Prize samples, when we collect the supernova and analyze them, we've had to actually compile samples that were collected roughly at different redshifts, mainly because this is coming from the fact that you need to design surveys differently with different observing strategies to catch the low redshift supernovae, which were typically more volume limited. We need to cover more area on the sky, whereas when we go for high redshift supernovae, we really want to drill deep. And it's the difference between the low redshift and the high redshift that really gives us the leverage on the cosmological parameters. So for Pantheon Plus, which I'm going to be talking about today, one of the big things was to compile as many samples as we could that we trusted in order to build the biggest sample of supernovae, going way back in history, to also include the supernovae in galaxies that have visible Cepheids that can be calibrated with HST. For comparison, you've heard Maria Vincenzi talk about the dark energy survey. In that case, we're trying to potentially curate the low redshift samples that we use to a much more modern sample of low redshift supernovae. But what that means is DES does not constrain H0. But Pantheon Plus can help constrain H0, and I'll be talking about that briefly. So the original Pantheon from 2018 was actually, sort of in this long lineage of compilations that have been sort of adopted by the community and have been used as one of the pillars of cosmology, Type 1a supernovae. So I'm showing plots from the Planck collaboration, which they've used Pantheon supernovae. But this goes back to as early as, and this is not comprehensive, but the 2008 Union analysis, which compiled 3 different surveys. The 2014 JLA analysis compiled 5 different surveys. The original Pantheon was 12 different surveys at 1,000 supernovae, and now Pantheon Plus is 18 different surveys and now 1,550 Type 1a supernovae. It's actually a little bit more than that because we have 1,550 unique Type 1a supernovae. We have 1,701 light curves of those 1,550 1As. So we have many supernovae that have been observed by different telescopes at the same time. So this provides an interesting cross-check. But what that means is in order to do that, we've compiled 18 different surveys, as I've said, 25 different photometric systems, because some of those have been recalibrated over the years, and 105 different filters. And what this means is we now have an average of 2 different photometric systems for every supernova that is in a Cepheid host galaxy. So that's 80 light curves of 42 hosts. Okay, so just a quick reminder about how things had worked in the past with the distance ladder. So up until 2016, the Shoes analysis did the distance ladder as follows, where you have absolute geometric distances in the first rung of the distance ladder. We tie those geometric distances to calibrate the Cepheid period luminosity relation. The calibrated Cepheids are then used to transfer that absolute calibration, distance calibration, to the Type 1a supernova intrinsic magnitude and calibrate that to an absolute distance. And that's done in the second rung of the distance ladder. This is one of the main rate limiting steps. You need to wait for the supernova to go off nearby in the middle rung of the distance ladder. And then in the top rung of the distance ladder is when you really get to measure H0 with the supernovae out into the Hubble flow. Now, in 2016, the second and third rungs of the distance ladder were treated independently. Adam Rees and his team went and analyzed the supernovae in the Cepheid hosts with different codes and different pipelines and analyze their systematics separately from the ones that were in the third rung of the distance ladder. One of the key points that we've done here with Pantheon Plus is to marry the two analyses by analyzing all of the supernovae in both the second and the third rungs of the distance ladder simultaneously, and propagating covariance and systematic covariances through both rungs of the distance ladder simultaneously, because it's really differences between the rungs that can cause issues with H0. If all of our supernovae are off by 100 magnitudes, but they're off by 100 magnitudes in the second rung and 100 magnitudes in the third rung, it all cancels out in the calibration. So the key thing is to characterize the differences and the covariances between the rungs, which is now what we're doing in Pantheon Plus. So what this means is now we have 42 supernovae in the second rung, and they're also included on our Hubble diagram, which I'll be showing today. And you can see how this has grown over time. And we can talk about the implications of that for LSST as well. Now, when it comes to measuring dark energy with the Hubble flow set, this has been done by a number of previous analyses that have combined samples. And what you'll notice is that each of these previous analyses, the joint light curve analysis, the dark energy survey 3-year analysis, and the Pantheon 2018 analysis, all were pushing against the systematic floor. And so when we're talking about LSST, and you see that for years we've been pushing against the systematic floor, you should already be worried we've got a lot of work ahead of us. But I don't think that this is a coincidence that each of these has had similar systematic uncertainties and statistical uncertainties. I think this is an artifact of how you go about your analysis. You have your data set, you realize you need to work on understanding systematic uncertainties until they reach a similar level of your statistical uncertainties. And then you realize, well, I don't get as much bang for my buck anymore, spending my time trying to push down the systematics below my statistical uncertainties. So I'm not totally surprised by this. And we'll talk about how we will be able to push this down for LSST too. Okay, so today and Pantheon Plus and Shoes have made some bold claims. One of the main ones I want to talk about and hopefully convince you of today is that we've pushed down the error floor and we have a factor of 2 improvement over the original Pantheon shown here in yellow when it comes to measuring the equation of state and dark matter and ordinary matter, mega matter. So this has been an effort over the last 5 years. In I think the last 2 years, we've released 10 papers. We're a relatively small team. We'd love to have you involved if you want to be involved. We're largely early career scientists, and I'm not going to be able to go through all of these papers today, but I want to hit some of the key highlights of the things that we've learned that will directly impact how we go about analyzing LSST. So the first thing is, we think we now have a better understanding of how host galaxy dust or circumstellar dust impacts supernova cosmology. Number 2, we think we have a better grasp on how important photometric calibration is, and in fact, is very important. And then number 3, bending is sinning. So some of these you've heard about this week in passing, but I want to dive in on these things and just hopefully try to make it as clear as I understand it. Okay, so there have been a couple of key questions in supernova cosmology that we've been attempting to address. Number 1, what drives the observed colors of the 1As? So you can see here, this is the SALT-2 color of the supernovae. It's just a histogram, and you see it's an asymmetric Gaussian skewed towards the red side. Another question that we've had to deal with is what drives the fundamental underlying scatter of the type 1A supernovae. So when we put them on the Hubble diagram, account for all sources of modeling and measurement uncertainties, we're left with a residual scatter that is not encompassed by our error bars, and we have to characterize that somehow in our lack of understanding of how type 1A supernovae can best be standardized. And lastly, what is driving residual correlations in the standardized brightness with the host galaxy properties? You've heard about this a couple times this week. I'm not going to go over that again. But what I want to point out is in putting together the Pantheon Plus sample, we found a number of key clues to help us answer all of these three questions. So with the 1500 supernovae, we're seeing three whopping signals that people really, for the most part, haven't seen before, certainly not to this degree. The first one is that there is a kink in the color luminosity relation between the blue and the red supernovae. So on the left side of these plots are the blue supernovae, the right side is the red supernovae, and you can see on the top, I'm plotting residuals to the assumption of a single color luminosity relation. And you can see kind of a kink on the blue side, which suggests that there's at least two, maybe more ways to describe the color luminosity relation differently for the blue supernovae versus the red supernovae. So that's one clue. A second clue, that first clue is 8 sigma significance. Second one, 11 sigma, is we find that the observed scatter in the Hubble diagram, the intrinsic scatter, is color dependent. So we find that the blue supernovae have the least amount of scatter in the Hubble diagram. And as you go redder, you find that they have more and more scatter. And this is after accounting for selection effects. We model our selection effects in the sample of 15,000 supernovae, 1500 supernovae, and correct for that. So even after that, we're left with this residual color dependent scatter where it's more for the red supernova. And then the last one, the 4.5 sigma effect, is what if we now split the mass step up, or the residual correlations in the Hubble diagram, with host galaxy properties? Today I'll be talking about mass, but we've seen this for other properties as well. What if we split that up and calculated it as a function of color? And so we've done it, and we find that there is no mass step or correlation with host galaxy properties for the blue supernovae, only the red ones. And so if you think about dust being the solution to all three of these, you can explain all of them with relatively simple characterization. The first one being that there is an intrinsic color luminosity relation that is described by the blue supernovae. They are unextinguished. The ones on the left side of these plots are not affected by dust. They have an intrinsic color luminosity relation. They have intrinsic properties. And as you go redder, you are dominated by the color luminosity relation of the dust, which happens to be different from whatever is the color luminosity relation of the blue supernovae, the intrinsic color luminosity relation. Now for the middle panel, you can explain the increased scatter in the Hubble diagram as a function of color by variation in the dust attenuation law RV, which we are not currently accounting for in the SALT2 model. And if you're not accounting for it and it's varying, it's going to add scatter in your predicted distances, and it will add increasing amounts of scatter the more dust there is. So as you go redder and there's variation in dust properties, the impact gets worse and worse. And lastly, we can explain the fact that there is no mass step for the blue supernovae because the mass step is driven by dust properties. So what this would imply is that different mass hosts have different dust properties. Or if you are looking at other tracers of host galaxy properties, you could infer that back to tracing the dust properties. Let me sort of hit that home a little bit more. So this is that bottom plot again. Sorry, no, this is the top plot. So this is residuals in the Hubble diagram as a function of color, but now I'm splitting on mass. And what we find is there's no difference in the data between low and high mass for the blue supernovae on the left side. And as you go redder, there's difference in residuals in the Hubble diagram. That is this is the same exact information as a color dependent mass step. But here now you can visualize it and you can see that what this would imply is that different mass hosts have different RV properties. So in the red, we have low mass hosts typically having higher RV dust. And conversely, the lower mass hosts, the blue data points, typically have lower RV. So we have a model that can describe this now, and it makes a couple key predictions. Those predictions are to reproduce the amount of scatter that we see in the Hubble diagram, you actually need a lot of variation in RV. And so this is one of the things that we can go and test, and others have gone to test. It predicts that RV should vary with the mass of the host galaxy or whatever other tracer you're using. And lastly, we would expect, if we're observing in some bands that are insensitive to dust, that the mass step should go away. So one key thing I'll point out is Ariel Gubar's group in the Johansson et al. Paper did see all three of these predictions in the near infrared, and so we call it fully consistent. And Salim, who's a galaxy extragalactic dust person, finds that RV does vary with mass. So encouraging. So this is that plot again, the mass step versus color, and you can see now our model reproduces this trend. And what I want to point out is this trend is seen in the dark energy survey 5-year analysis that Maria talked about. It is seen in Brody Popovic's pan-stars plus SESS photometric analysis that he's worked on with 2,000 supernovae. These are really big samples with lots of supernovae, and it's being seen to really strong levels. So if you're going to come up with a solution to the mass step, I think at this point, it's got to be able to explain this trend. If you don't believe what I'm saying, I think you still have to be able to explain this. I'll leave it at that. Okay, so that's one of the first lessons learned. Second lesson we've learned is the impact of photometric calibration. So in putting together the Pantheon sample, we've cross-calibrated 18 different surveys using the Pan-STARRS All-Sky catalog because it overlaps with all of those 18 different surveys. And what we've gone ahead and done is allowed the 0 points for all of those surveys to float. We compare the overlapping stars, and we put priors on each of the surveys based on how much we trust their own individual calibrations and solve for a common solution. And this means we're actually floating the calibration of Pan-STARRS while it's the intermediary between all of the other surveys that we're comparing with. And what that means is we end up with a covariance matrix, and we use that covariance matrix. It's a filter by filter covariance matrix, and we use that for cosmology. We also use it to help inform the training of the SALT-2 model, because we want to incorporate these calibration uncertainties in the model training as well. And the key thing that I want to point out that we found is that when we account for these uncertainties in the model training and the fitting simultaneously, and when I say simultaneously, I mean consistently. So in Pantheon 2018 and the Dark Energy Survey 3-year, that was not the case. The SALT-2 training systematics were analyzed independently from the fitting calibration related systematics. And we thought, going and doing this, that if we are consistent with our systematics in calibration, when we put them in and train our SALT model, and when we fit the light curves, we would actually hopefully reduce the size of the systematic uncertainty. That's not the case. When we are consistent between training and fitting, it doubles the size of the systematic uncertainty when we account for this covariance. And so that's important for really stressing how important calibration is for the future. One of the last lessons I want to talk about briefly is a paper I wrote with Sam Hinton and Dan Skolnick called Binning is Sinning. It's kind of inspired by a couple of other papers in the literature over the last couple of years. So we called this the supernova version. So the original Pantheon binned its data set as a function of redshift. The Rubin science requirements document followed the methodology of Pantheon 2018, okay? And I'm gonna tell you that I don't think this is the right thing to do. So fundamentally, binning loses information. If you have some systematic, it doesn't matter what that systematic is, it may have some beautiful trends in supernova color, but if you bin the data set as a function of redshift, that systematic can look like the bottom, which is residuals and distance as a function of redshift. And that slope right there looks like cosmology. It looks like you could get your equation of state of dark energy wrong and mistake this systematic for cosmology. The problem is we knew that the systematic had all this beautiful color information in it, and there is no cosmology that changes your colors like this. So you're losing information fundamentally. And so if there's nothing you take away from this talk other than that, I'll be happy. Try not to bin your data sets. I think I have time for this. I want to just visualize this with a little bit of math and some corner plots. So if you take your nominal analysis, MNOM, that's your set of distances with your nominal assumptions. You take some perturbation to your analysis, which is your systematic. It's like a derivative to your nominal analysis. And you can scale that by any arbitrary amount. You typically put a prior on that given your prior knowledge of the size of the systematic. Let's say it's, I feel like I know G-band calibration to 1%. That prior would go on S. And you can compare that to cosmological model, and you can see, is that systematic degenerate with the cosmological model? So you can fit S and cosmology at the same time. And what you find is if you bin your analysis, you can't constrain S very well, but if you don't bin your analysis, you get the blue, light blue contour. S is constrained down in size. The data itself is what we call now self-calibrating out the size of the systematic uncertainty. And in this case, it's a color-dependent systematic uncertainty, and you reduce the degeneracy with cosmology. Now, if your systematic happens to be purely redshift dependent, then you don't get this benefit. And so what we found in real data on the Pantheon Plus analysis is that we do see quite a large reduction in the size of our systematic uncertainties simply by not binning our data set, a factor of 1.5, which is just whopping, and that this effect does not reduce the size of our redshift systematics. So the importance of actually sources of redshift systematics is going to become even more important. And I think we're going to have to rethink what our priorities are when it comes to systematic uncertainties in LSST. So at the end of the day, we've been able to measure cosmology. We pushed down on the error floor, and in an effort to save time, I'm just going to breeze past this. You can look this up in the paper. W is consistent with -1. Okay, but the kicker is that for LSST, this self-calibration ability grows with the size of your data set. So this is only for systematics that are not purely redshift dependent. But if your systematic has some other dependence in it, like color, as your data set size grows, which as we know, that's coming for us, that's great. You actually get free, you get benefit on your error budget, your systematic error budget for free. You don't have to think. We haven't been able to really think like that we get this free reduction in systematic uncertainties without thinking. So as long as you're careful with your analysis, I believe you will get this. And so that's really exciting for the future of LSST. This is a bit of a cheeky plot, but I just put the LSST science requirements document constraints on top of the Pantheon Plus W not WA, and you can see that we have potential to find exciting results with LSST. And in fact, with this non-binning approach, I believe that we will get even better constraints than what we're seeing here. So that's really, really exciting. Now, we're about to end the conference. I just want to take a step back because we're kind of wrapping up here and we're heading to desk next week. And I want to just kind of get us all excited because I don't think, I probably should think about this more often, but every time I do, it kind of just blows my mind. And I also like saying this kind of analogy to our non-transient friends in cosmology, because I think the future is actually potentially the brightest for the Type 1a or the supernova cosmology, because if you compare the data set from DES, so out to roughly redshift 1.1, 1.2, weak lensing had 5,000 square degrees, and they're going to 18,000 square degrees with LSST. But for DES, the supernova group had 30 square degrees, and we're going to 18,000 square degrees. We can't know I still can't comprehend that. I don't think the other people in weak lensing realize that we're really like this. We can't. Yeah. So I don't know. Just that really excites me. That really excites me and makes me. Sometimes I wonder, like, should I be working on weak lensing? No, this is awesome. This is really awesome. So, and it should, you know, we shouldn't be thinking about the Hubble diagram anymore in the sense that we've been thinking about it, right? Every day I ask myself, like, if W is just -1, what am I doing? But so we've sort of been drinking from this proverbial watering hole over here, measuring the Hubble diagram, collapsing the whole sky down to these 2 dimensions, distance and redshift. But we should really be looking at the whole sky, and we're going to be able to do this. And when we look at the whole sky, we're actually like really significantly statistically starved. And so that's where we get this huge benefit from LSST. We can start testing the growth of structure. We can start looking across the sky in different directions, measuring isotropy and proper motions, looking at our local neighborhood. We can measure voids and clusters with the supernovae. We can measure host galaxy properties. We can measure potentially properties about our own Milky Way. And we can do these all sky cross correlations, just like all the other probes are doing their 7x2 point analyses. We get to be one of those. And this is taking it to the next level. And that's where we're going. And that just really excites me. So yeah, with that, questions.
Thank you. Thank you for being flexible and starting the talk on a moment's notice. I appreciate it. It's always stressful. Yeah. Questions? Yes.
There's a question from David Jones on the Zoom. So David, feel free to unmute and ask it.
Great, thanks. Yeah, I was going to type it out, but if you don't mind, really great talk. By the way, I wanted to ask a slightly long-winded BS20 question. So I'll just start off by saying, you know, BS20 is amazing. I totally agree with you that anyone who wants to understand the mass step now needs to reproduce this color trend, which is just a huge recognition that that helps a ton with scatter and cosmological constraints, and also really points to the physics of the thing. But I wanted to kind of just ask, when you think about the kind of papers looking into BS21 lately, you have, I guess, Popovich 2021, which had like a 1 sigma mass step remaining with like too little RV variation to quite take it to 0, but it's only 1 sigma. Then you had the near infrared papers where Johansson et al. Had a mass step in the Y band that was the same as the mass step in the G band, and it doesn't really disappear until H band, which isn't really what you'd expect from dust. And then the other near infrared papers, I think there were like 3 others that still had a mass step in the near infrared. And then these recent 2 host galaxy papers, which also kind of, one of them, I think, left a 1 to 2 sigma relation remaining after correcting for the RV variation in host galaxies. And then the other one said that they couldn't fully explain the correlation with host galaxy color. So anyways, sorry for being super long-winded. Is your sense that the mass step is still totally explained in these kind of 1 sigma remaining mass steps from some of these host galaxy analyses are just statistical fluctuation, or do you think it's, you know, do you think there's still more there?
Yeah, I think that there's subtleties to all of the different papers you pointed out. I do think that we've gone from 7 sigma to 1 or 2 sigma is a whole different, we're having a whole different discussion than we used to be having. So if at the very least, if we've changed the discussion a little bit, I do think that that's a step forward. And okay, so in terms of seeing some residual mass step in the near infrared until H band, I think one of Dan's students is trying to simulate this. So basically take the BS20 scatter model and simulate it out into the near infrared, and is finding that you actually could see some residual mass step all the way out there. So maybe I made it too strong of a statement that it should be 0 in the near infrared. I don't know how far out you have to go. Yeah. The last thing I'll point out is that the near infrared data sets are small, and so it's, to me, difficult when we're talking about 2 sigma effects with smaller data sets. Like I at the moment am sticking to the larger ones and the signals I see in those and sticking with that at the moment.
There is a question from Consta
Thank you.
online. Can you unmute and ask it yourself?
Yeah, thank you so much for talk. I'm sorry, it would be a very naive question because I know very little about 1A cosmology, but since it's an invited talk, I allow myself to ask naive questions. So I have 2 actually short questions. How reproducible is Pantheon Plus? So is there pipeline code published and data? And the second question, how are you dealing with, so it is quite related to binning, but from another angle of view, how to deal with different, when you have a single supernova observed by 2 surveys, do you feed it with a single feed, or are you doing 2 feeds and bin it somehow?
Okay, I'm not sure I caught, sorry, can you repeat the first question?
How reproducible is Pantheon Plus? I mean, is code published and data?
Yes, okay, so so the code is now on GitHub. The paper isn't officially accepted, but it's at the point where it's not changing, so I'm just waiting for them to kind of click the button. So it's now on the internet. So it's reproducible in so we've included our Pippin input files. So if you've done any supernova cosmology with SNIa or Pippin, you in theory could grab the file that takes from start to finish the whole analysis. But at the very least, you can look at all the pieces that went into it and dive into the various individual pieces and see what we did there. But it's fully an open book. It's fully an open book. And the data, the light curves, the light curve fits, the simulations, the likelihood is all on GitHub. There was another question, but I didn't catch the one either. Sorry.
We'll take another question from the audience here.
Yes, sir.
Excellent talk. Very clarifying. Can I just ask you to elaborate about unbinning and the computation that we need to analyze for cosmology, and especially in LSST time? Are we going to be eating the resources that the cosmology, for instance, desk is going to have, or would you predict?
Yeah, so it depends. Good question. So yeah, how do you invert a 1,000,000 by 1,000,000 matrix? So there's a couple workarounds that we've thought about. Rick's working on if unbinning is sinning, then is rebinning forgiving. Basically, like seeing in what dimensions you can sort of collapse the information back down without harming your constraints in the effort of making it computationally feasible. The other thing is, so for JLA, you had to invert the matrix every step in your likelihood. For Pantheon Plus, we actually don't have to. So you just have to do it once, and you just save that. So depends on what you have to do for LSST, what route you go down. Yeah.
Let's thank the speaker one more time.